section 7.6. Now 7.6, again, is really similar to 7.5. We have the same kind of pattern. I want you to look through the section to see how they got there. Again, it's important to look at the differential equations and how that works, especially if you have not had diff-EQ. But one important thing to note, we're talking about an RL circuit now. When we talk about inductance, it's current we focus on. So the current before time zero, the current after time zero is equal because current in an inductor cannot change abruptly. So capacitor, voltage, inductor, current. I want you to remember that. And then we get the same general equation, except with current, and with the fact that tau equals L over R. So the way we solve these problems is the same. So let's jump right into an example. So first I want to find my initial current. So initially this switch is closed, right? And I have a circuit that looks like this. So for t less than 0, I have a DC circuit. Switch is closed. Inductor looks like a short. So I have this circuit. And I want to know the voltage. I'm sorry. We're looking for the voltage finally across this, but to get to the voltage, we're going to find the current, right? Because we're talking about an inductor. So I want the current across there. So what is my, or did they give us that? Because I don't remember working that out. Oh well, we can find it. That's not that hard, right? So we're looking for I of 0. Well, that's the current through this resistor. So if we knew the voltage here, we could find that. We could do that voltage pretty easily with nodal. So let's write in all our resistor values there. Let's call this V of X and do nodal. So I have 2 amps entering. Again, we're using nodal. Minus 2 plus Vx over 12 plus Vx over 20 plus Vx over 6. That does not say plus. Getting a little crazy with my x's. Plus Vx minus 20 over 5 equals 0. If I solve this, I only have one unknown. I get Vx is 12. So my voltage across here is 12. And that means my current is 12 over 6, or 2 amps. So that is my initial current. I need my final current. I'm going to go ahead and switch colors. So we want to find our I of infinity. All right, switch opens. So we are really just looking at this circuit here. 20, 6. This looks like a short. We have 5 and 20 volts. So I want this current. It flows through there. 5, 6, 20. What do you want to do? Nodal makes sense again, right? Calling this node Vy, if I want to here. So we have Vy over 20 plus Vy over 6 plus Vy minus 20 over 5 equals 0. And unfortunately, I don't believe I have worked that number out on here. So Vy equals something, and then my I of infinity is Vy over 6. That something over 6 turns out to be, this is kind of a mess. But it looks like it turns out to be 1.6. 1.6 amps. Okay, so that's our final current value through our inductor. We also need our tau. Let's switch colors again. We'll find tau in blue. We need to find tau. Tau is L over R. This is after the switch has opened. So we're looking at this circuit. This is just after the switch opened. Like that. So I need, again, an REQ, right? We can draw the 20 in, we don't have to. It's not going to make a big difference for us. So my equivalent resistance, 26.5, is going to be what? Well, I guess I really shouldn't draw that in. I don't want to confuse you. So let's go ahead and draw that as a short. So we're deactivating that to find our equivalent resistance. Deactivate that by making it a short. So now you can see that 20 and 5 are in parallel. They share this node, they share this node. And the combination of those is in series with the 6. That gives me 10 ohms. So now my tau is L 0.5 over 10 or 50 milliseconds. And now we're ready to plug that all into the final equation. We'll do that with pink. I have I of t equals I of infinity, which is right there, 1.6, plus I of 0, 2, minus I of infinity, 1.6, e to the minus t over tau, 50 milliseconds. Or writing that nicer, I get an I of t that's equal to 1.6 plus 0.4 e to the minus 20t. But we were asked to find v of t. So we need to use from chapter 6 that v of t is equal to L di dt. So you need to take the derivative of this with respect to t, multiply it by L. Again, I'm going to trust that you can do the calculus. I hope that that's true. And we'll get this. You know what? Let's go ahead and do the calculus just in case. So derivative of this with respect to t would be 0 plus this hangs out. And we multiply it by minus 20. And then we also have to multiply it by our L, which was 0.5. So there's where we get our minus 4. And we should do t greater than equal to 0. Amps. I always forget that part.